Okay, so now we've talked about distance and time, as well as mass, which are basic SI units, and then some of the derived units from them. Volume, derived from distance. Velocity, derived from time and distance. Acceleration, which you could either say is derived from distance and time, or it's a derived from velocity and time. And so that gives us some of those SI units. Now I want to talk about a few others. And those are, they have to do with energy and work. So energy, they have to do with energy and work. Both of these are very closely related, and you'll see why I say that, at least in my mind. So, energy and work. So now of course there's some equations we should have memorized at some point, and let's talk about those really quick. So what's work equal to? Work is equal to force times a distance. How much force you apply over a distance. Now, as far as energy or as work as well, let's talk about joules. What's a joule? A joule is equal to a Newton meter. Now, it's really important, at least for me and for you, I think, to do well, to be able to do little, what I call physics gymnastics, be able to jump back and forth and do little things that can get you from one to the other. Okay, now, as far as energy, let's talk about energy real quick. What types of energy are there? Well, in a basic level for physics, there's two types. There is a potential energy, and there is a kinetic energy. And you're like, oh, which one was which? I can't remember. Okay, here's how I remember it. If someone says, hey, that guy's got potential, it could be a positive thing, but in many ways it kind of has a derogatory component to it. If someone has potential, have they actualized their potential, or is that potential stored up somewhere and people are saying, you know, he's got potential, he's gonna be something today, he will get somewhere someday? It's potential energy. If he died and was buried, that potential energy goes with him to the grave. There's one of my previous professors talked about all the potential that's buried in the cemeteries around the world. Potential energy. When we think of potential energy, we usually think of like a gravitational component to it. You know, it's gravitational potential energy. So now kinetic energy, on the other hand, if someone wants to say, man, that guy's got kinetic energy, that means he is actualizing his energy. There's motion, there's movement, there's action, there's things happening. And that's how I remember that. Potential energy isn't happening. Kinetic energy is. So when we think of potential, we think of this equation: mass times gravity times height. So you've got this mass, and you've got this gravitational pull that's trying to pull it down, and this gravitational component is going to try and pull it a certain distance, and so that gives us potential energy. Let's look at this a little closer. Let's do some physics gymnastics here. So what is mass? We just learned that the SI unit in the previous video for mass is kilograms. Is that correct? Gravity is an acceleration, the Earth's acceleration, and we learned that acceleration is meters per second squared, and that's our acceleration. And then we learned that height has to do with distance, and our SI unit for distance is meters as well. So what that gives us is a kilogram meter squared over second squared. And that gives us an energy, which in this case is our potential energy. You're going to see something very interesting as we go on. Now let's go over and talk about kinetic energy. So kinetic energy, now as we just learned, that guy's got great potential. Well, no, that guy right there has got great kinetic energy. There is action involved, there's motion, there's something happening. So the way to remember that is this the one that has velocity in it. It has something moving, something's going on. And not only that, but when you move something, if something's heavy, it takes a lot of energy. If it's light, it does not take as much energy. So mass comes into play. 1/2 mv squared. And it's important to know maybe we'll talk about this later, the importance of velocity at kinetic energy is greater than the importance of mass because of its squared value. But once again, let's take a look at this and see what we've got going on, which I want you to see something. We'll ignore this constant for now, but mass, we learned that what's mass equal to? Mass, the SI unit of mass is kilograms. And then velocity, we learned, is meters per second, correct? But don't forget the square component, so it's meters squared, so top and bottom, times seconds squared. And so what does that do for us? That gives us kilogram meters squared per second squared. So look what we've got here. We've got these energy equations, where there's potential energy or where there's kinetic energy, that are the same. They have the same units. They're interchangeable. You can work with them. You can do little somersaults with physics. So keep this in mind as we go on. One last component we're going to talk about as far as this goes in this area for SI units, and there will be more, but this is the basics where we're going to start, is power. Now when I think of power, I think of what? When I think of power, I think of what? If you forget what power is, just think, what? It's a watt. Is the SI unit for power. Now you're thinking, oh, I don't remember what power was. Well, that's okay. Power, if you get your power bill, which I get a power bill now every month, and I try to think like what it's like the amount of energy I used over a certain amount of time. Okay, energy I'm not sure, but time is easy one. Time, that's cool. So there's a certain amount of time, and then there's some sort of an energy, or I guess we know that energy and work are kind of the same, as we can see here. Well, wait, hold on. So it's an energy over time, so it's probably the work it does over a certain amount of time. So my bill is trying to tell me how much work I used or energy I used in a month. Okay, that's good, and that's equal to watts. Now, if we want to go a little farther here, we know that work can be a joule. Is that correct? We see up here. And once again, we're kind of deriving some of this again. But I think it's really important to be able to do this, because if you can think through these things in this way, you'll be able to jump around and you'll be the one in charge instead of looking at a problem and wondering, what in the world is this asking me? What does it want? What information do I need? How do I solve this? And we're going to talk about what I call trigger points as well, things that trigger our mind to engage in a problem and to attack it, versus looking at a problem and not knowing where in the world to start. So let's keep going on here. So we know a joule is a Newton meter. Let's write this down here. So Newton meter. And we know that time is seconds. We'll change seconds or whatever, but same thing, seconds. So power is a Newton meter second. Well, we can actually take this a little farther, because we know that a Newton meter on our is a measure of energy, right? We learned that. Right here we learned that these little guys here are related. So instead of a Newton, we could actually put down a kilogram meter squared per second squared, right? So let me help you visualize this. And then, but we also have a meter left over here. Well, that's what a Newton meter is, excuse me. That whole component, excuse me, is equal to that. And then we also have an extra second right here. So we know that a kilogram meter squared over a second cubed is equal to power, and that's equal to a watt. Power is equal to what? And that's how I remember that. So keep these things in mind. Keep these little gymnastics, and I call them that because I think of these gymnasts doing these flips and turns and all this. That's what you can do. You got to learn to do these things. So when you view something, you're not just viewing some equation that you had memorized. You're literally viewing and seeing through it and seeing the concept. Well, work is equal to force times distance, and then because if you see just this, you're going to be looking in the equation for a force and a distance maybe, and it may or may not be there. There might be a Newton in there, there might be a kilogram or a meter or seconds or whatever, and you're going to get extremely confused and not know how to approach it. So keep these in mind as you approach it. You need to be able to turn this video off and walk through each of these and figure out how you can derive different things from each one of these components. If I had a kinetic energy, how can I get to a potential energy? How does that potential energy relate to work that may or may not have been performed? How does that potential energy relate to some power or to watts? What would the additional component need to be in order to utilize that? So think of things in that terms, and that's why I said initially, these videos are not where you're going to spend all your time. You will spend some time on them, but you're going to pause them, you're going to go and you're going to practice these concepts. And eventually, and hopefully by the time you see this, I'll actually have some links on here that will link back to some exams you can try. There's some online exams to get you better at it, and then possibly some more videos that go into a more detailed explanation of some examples and how to approach and attack them. So it's all about how you gain control over it instead of letting it control you.